Okay, now we're going to be being recorded.
Okay.
Okay.
So I guess Marcelo takes the...
Yes, let's start. Okay.
Yes.
Okay, so good morning and good afternoon. And on behalf of the postgraduate program in astronomy of the Observatório Nacional, be welcome to our special courses. So since in 1996, Observatório Nacional has had special courses dedicated to providing graduate students and postdocs with a broad view on select topics in astronomy, astrophysics, and cosmology. And each year, experts from different areas are invited to teach courses in their field of research. So this year we have a special edition focused on ongoing projects in which Observatório Nacional participates. So I would like to say thank you very much to all the professors for accepting our invitation to be a lecturer in this new edition of CCE, especially Dr. Mauro Salvato, our first lecturer. And also thanks to all the organizers, Dr. Daniela Lázaro, Dr. Simone Daflon, Dr. Fernando Roig, Dr. Jailson Canizzi, and Dr. Renato Dupik. So let's enjoy our CCE and be welcome. Please, Renato.
Okay, thanks, Marcelo. Welcome, everybody. So to avoid further delay, I'm going to go start introducing Mara Salvato. It's a great pleasure to say, to introduce her to you. Mara, she finished her PhD in Potsdam in 2002, did some postdoctoral work at the Max Planck Institute for Extraterrestrial Physics, the MPE, in Garching. Then Caltech, became a junior researcher at the Plasma Physics Institute, also, I hope that's correct, also in the neighborhood of MPE. And since 2012, she's a scientist at MPE. She has, I'm going to just say a few words. She has a very huge CV. She's a member of several collaborations, including Euclid, Athena, SDSS-4, Spiders, SDSS-5, Candles, EMU, Stripe 82X, Vendors, Cosmos, JPass, foremost, and especially she's significantly involved, and of course, that's the subject of the talk, in the extended ROentgen survey with an imaging telescope array, also known as eROSITA, and where she is a co-chair of the eROSITA German part, in AGM Science Working Group. She's chair of the eROSITA Follow-up Infrastructure Working Group, and I guess I'll just, she can say more if she feels like it. And she's going to be talking today about eROSITA. And our context, so that people know RON, is that we have an agreement with JPass for common areas of the sky. So I think the students and early career researchers will probably find this very interesting. And if they want to contribute, they will know where to start from. So I'll pass the word to Mara.
Thank you, Renato. Thank you very much for the kind presentation. It is really an honor for me to be here today. It's actually, I feel it like a strong responsibility to be the first speaker of the day. As I already was mentioned, I will speak to you about eROSITA today, what we are learning with the instrument, and I am spokesperson of the eROSITA, the A part, and I'm actually giving the talk on behalf of the collaboration. Here you can see those people that met in person last week. We had the first in-person meeting after 2.5 years of COVID, and you can see how many young faces are. It has been really an exciting time, and I hope to be show you some of the interesting things that we are doing. It is morning for you. Probably many of you are still drinking your coffee and you want to start slowly the day. So just enjoy this picture first. This is the X-ray sky as seen by eROSITA after the first 6 months of observations. In red, you have the soft energy emission. In the blue, you have the hard part that when the soft has been absorbed by different type of material. You can see extended sources. Most of them are supernova remnant, but you can also see the Virgo cluster here. You can see the supercluster from Shapley, and most of the dot sources are actually supermassive black holes in our supermassive black holes from galaxies, or small black holes from stars in our galaxy. I would like that you have this picture in mind and you have the numbers that are sinking in the brain. We have in just half of the sky, I'm going to speak only of the results found in this part of the sky, which is the one that is analyzed by the German collaboration. In that half sky, there are 13,000 confirmed clusters. We have 1.1 million supermassive black holes. Just to keep in mind, this is twice as many supermassive black holes as have been observed in the last 20 years of X-ray astronomy, and we have 140,000 stars. Essentially, this slide is my outlook, if you like, of the talk. I'm going to speak of all the events that are visible in the X-ray sky, from the circogalactic medium, AGN, X-ray binaries. Of course, I will speak about large-scale structure and many other things. And I will either show what we are already finding or the potential of what we want to do, but it is too early to give you some result. Before starting with the results, let's keep in mind what eROSITA is. Is a German instrument, mostly built at NPE, but in collaboration with many other German institutes, and it is flying on a Russian satellite. The instrument has 7 telescopes. Each telescope is formed by 54 cylinder nested mirrors, and each telescope is attached to a camera. Because of the complicated optics, you have here on the right side how the PSF of the instrument appear. And of course, it looks much more focused in the center. And then on the outer part, you have some aberration. But we can control that. We know how to deal with that. And I will show later how. So in general, you have that for the half energy width, which is correlated to the PSF for people that are used to optical words. We have 18 arcsecond in pointed observations. And when we do survey, because we are averaging over images with different quality, we reach 30 arcsecond. The energy range is between 0.2 and 10 keV. And it has this spectral resolution. An important point to remember is this, and this will come over during the talk in various moments. It is the best CCD camera available in space at the moment, and it has a very high spectral resolution, higher even than XMM. It is shown here in this picture where the supernova 1987A, the spectrum of it, is compared between eROSITA and XMM, and you can clearly see how with eROSITA you can perfectly disentangle the various emission lines that are not visible with XMM. One other thing that you have to keep in mind is the field of view of eROSITA, which is large and it is tuned for making a survey instrument. And most importantly is the fact that our background is stable and homogeneous. And all this effect is going to play an important role in the science that we wanted to do. In order to convince you of the importance, for example, of the stable background and the importance of the large field of view, just look at this image. This is the XXL North survey field observed by XMM and by eROSITA. And XMM, even if a lot of effort has been spent in order to create an homogeneous image, you cannot avoid to see the connection between the various pointing. And this is going to affect your science in the moment in which you want, for example, to have a selection function that take into account the sensitivity of your surveys. And this is not a problem with eROSITA, where you can see the same piece of sky. Every source that you can see in XMM is also seen in eROSITA, but in addition, what you have is that really the background is homogeneous. And this makes life much easier when, as I said, you have to think to a selection function. Again, here, the large field of view give you, you immediately understand why it is important. If you wanted to study, for example, merging clusters, you will need a different pointing with XMM, for example. With eROSITA now, you have not only the entire merging system, but also the surrounding environment. You can see clumps, you can see group of clusters, in addition to all the dots in the background that are again AGN. This is again the same image, but this time in 3 colors, the RGB image, and you can already see there is something that is connecting the two systems, the two Hubble systems. And this image was actually taken during the calibration phase, where we wanted to test the quality of the instrument, and the goal was to see whether we were able to detect the filaments connecting this system that eventually should merge into one, and indeed we were able to identify it. So we found the connection between the two with a reliability of 11 sigma, so definitely a confirmed one. We can also see the material that is unfolding into the system, exactly as theory of cosmology or galaxy formation, cluster formation are expecting. An important point that I will bring up also later is the fact that these results are not done with X-ray alone, but they are always done in connection also with multi-wavelengths, and in particular case here for the detection of the sources, understanding what we were looking at, the work has been done combining radio images and optical data. An important point to remember from the beginning is that eROSITA means the science driver is cosmology and large-scale structure, with the idea that the clusters are the tracer of the growth of the structure, and you can easily detect the clusters thanks to the hot plasma in which they are immersed. So with the X-ray, you don't see the cluster, but you see the plasma that is surrounding them. And the idea of the beginning was that in order to contribute to cosmological analysis, you needed to have at least a complete sample of 10,000 massive clusters and being complete. And the level 0 cosmological probe, if you like, is the cosmological question is which of the many cosmological models that we have currently available is the right one. For those that are not familiar with the topic, let's give a simple sketch, if you like. What you see on the right panel, on the right side of this figure, you have the representation of the local universe, redshift 0, as it is seen from the various cosmological simulations. All these simulations are very similar to each other at the local in the redshift 0, and they are in agreement with observations. But as you can see, they have a completely different way of arriving at redshift 0. Redshift 3 and redshift 1, they are completely different. And one way to test the method is to see simply as a function of redshift, what is the number of clusters split in mass, for example, and then see, depending on which cosmological model you use, or which is the one that fits better the data. So that will be level 0 of our analysis. And we believe that with our numbers, we are going to be able to provide accuracy in the cosmological parameters at the sub-percent level, and limited by, not limited by the statistics. Just to give you an idea how big leap forward is these 10 to 5 clusters. Here, these are all instruments, surveys that are used for detecting cluster with the same purpose. And these all use the detection, if you like, of the intercluster medium for the analysis. And you really see that you go from a few thousand objects or few hundred, and really eROSITA is the one that is making the leap forward. In order to prove that we were actually reaching that quality, so the 10 to 5 massive objects were the requirement for building eROSITA, and then the question was, did we reach that level? And in order to do that, before starting the all-sky eROSITA survey, we decided to observe 140 square degrees of sky at the depth that eROSITA will have at the end of the mission. We speak later about what I mean with the end of the mission. So these are the largest contiguous X-ray observation ever had beside the all-sky. And you can see here that we have detected 28,000 X-ray sources, and 477 are actually clusters. And among those, there are already 19 superclusters. If you remember, very few superclusters were known. Actually, one is now in the IFES, and this is the supercluster with the higher redshift ever detected. I believe it is 0.36, but I will need to check, but it's for sure the one with the higher redshift. And what you see here are the X-ray sources here in the zoomed area, and you see how they are, sorry, here in red, and you see how they are consistent with the density map coming from the optical images of hypersupreme-cam. And these resemble very nicely the simulations that we are usually using for trying to understand how our universe has evolved. From these 140 square degrees and 477 clusters, we are now in the situation of having, for the first 6 months of eROSITA, 26,000 extended sources, in addition to the 1.1 million of point sources, and 13,000 of them actually have already a redshift confirmation. So these clusters are already understood. For identifying the cluster, we have used a patchy approach. So we used all the deepest data that were available in that part of the sky. So Legacy Survey DR9, the Noir Lab Science Catalog DR2, the KIDS, the PANSTAR, and so on. We have the higher redshift at 1.49, which is also confirmed. So we are reaching a high redshift as we wanted from the beginning. And what we are doing now is making a cleaning of the catalog to make sure that we are considering really the real clusters and for our analysis. If you wanted to, one thing to say is that the first analysis done with this patchwork of data, as I was mentioning, and this is creating some extra work when you wanted to create again the selection function for your analysis, because you have to take into account the different depths and try really to understand many implications. And particularly this week, the Legacy Survey DR10 is becoming available, and as you will see later, this covers the entire sky seen by eROSITA with a sufficient depth in order for us to make our science. I will go back later to this point. Here you see the preliminary distribution in luminosity, mass, and redshift of our clusters. It is still not yet calibrated, just for visual purpose to show you the distribution of the sources. What is important to say is really that we are getting all the massive objects above 10 to 14, but we are also having plenty of objects in the low mass regime, and these are completely new parameter space for understanding astrophysics in clusters. Not only cosmology you can do with the cluster, you can do many other things connected with cosmology, search for dark matter, detection of the WIM, galaxy evolution, and you have plenty of questions that you can answer. I'm not going to show you any result yet, because in order to answer this question, you needed to, as I was mentioning, cleaning your catalogs and make sure that all the systematics are corrected for or considered, and we are almost there. We had at the last meeting some preliminary results, but it is too early to show them to you, but I promise you we are getting there, and soon you will see some of our results. One interesting thing to say about clusters is that despite they are usually seen as extended in the X-ray images, they can also be unresolved and appear as a point-like. It was our surprise, if you like, when looking in the IFED's catalog of point sources. We have plotted all the 22,000 objects, depending on the cut that you do in detection likelihood. This plot has only 22,000. You see here all the point sources. You have the stars here below this line, and you have here AGN, color-coded as a function of the redshift that we assign to them. And for guiding your eyes, you have the track of evolution of different type of galaxies. So you see that here you have the clusters, here you have the quasars with a higher redshift here, and then you have depending on the level of the extinction, you are going to populate this area, and then you go back to the low luminosity AGN, and finally you arrive to a region where the data are actually fit best by an elliptical template or an S0. So you see S0 and elliptical. This was kind of strange. And what they came out is that looking then at the images came out that we were actually looking at the BCG of clusters. So these are additional 300 candidates clusters, and about maybe 100 or so are secure. So just looking into the point-like source catalog, we are increasing the population of clusters that we can study. Speaking of surveys of AGNs, let's put things a little bit in a context. Here you have the typical pencil beam X-ray surveys done for detecting AGNs. You have the area and the X-ray flux, and you have here in magenta the surveys that are done with Chandra, in blue those with XMM, and green those that were done with Rosette. And already after the first 6 months of eROSITA, we were already 8.5 times deeper than Rosette, and finally with ERAS-8 we are going to be 25 times deeper than that. And for just for keeping you for your reference, this is the depth expected for all sky and at the pole at the end of the mission. An important point that often we forget is the fact that for the first time we are also going to have the all sky survey in the hard band, and this was something that we do not have yet. And just to give an idea of the population that we expected to have, this is an old plot where we show the luminosity and redshift of AGNs from the pencil beams, and you see here the area filled with the eROSITA data. We are going to detect the most luminous quasar responsible with the feedback of the current local scaling relations. For these objects with enough photons, we are going to be able also to get the spectral analysis. We are going to have tens of thousands of low luminosity AGNs that help regulating with the feedback, the intergalactic median, and the formations, star formation in small groups of galaxies. But most importantly, with these millions of objects that we are having, we will be able really to split the samples as a function of some parameter and see evolutions that before were not possible. Essentially, normally what we say is that eROSITA is going to be for AGN evolution what Sloan has been for studies of galaxies. And in this plot, I'm still showing you expectations simply because for making this plot with the data that we have in hand, we needed to have the redshift, and we are still working on it. Speaking about redshift, this is one of the results that is going to be submitted probably this week. One question that was always open was about the type 1 AGNs and the origin of the soft access in the X-ray bands, and there were essentially three theories that try to explain this excess. And our goal, maybe naive, was to be able to finally decide which was the right model. And what is coming out is that we have 30, 30, 30, and all the three models are able to explain different type of objects. So now the question is really try to make sense of the finding and possibly extend the sample, considering that the work done here was done on IFEDs, while now just with the ERAS-1 we have 180,000 new objects are selected for which we can do the analysis and really try to understand whether maybe there is an evolutionary path that explain how to go from a model to another. I was telling before, the importance is large field of view, homogeneity of the background, spectroscopic capability. This is a slide that underlined once more the importance of having large area, not only for seeing completely an event like the merger of a cluster, but is also the large area is fundamental for detecting rare objects or objects that have a very short lifetime. This is the case of the obscured AGNs in a feedback phase. We have that galaxy evolution theory predicted the existence of this phase and feedback, where you have high accretion on the black hole, you have strong wind, you have outflow, and you have this that this event is very short in life. And this is one of the objects selected for representative of the population of objects in feedback, presented by Marcella Bruce et al. This is the object. You can see that from the X-ray spectra, indeed, the object is clearly a quasar obscure, so type 2 for those that are not familiar with the terminology. There is a high accretion rate on the black hole, and if you look at the optical spectrum, you can clearly see that the oxygen line, instead of being narrow, they also have a broad component indicating that there is a outflow. This is a strong evidence of it. And we are expecting to find 500 of these objects, and we have already 24 confirmed in IFEDs, and the paper will be submitted this week by Blessy Musimenta. And with all these samples, we will be much closer to understand how galaxy and AGNs are evolving together. Another important contribution of eROSITA to our understanding of galaxy evolution, if you like, is the possibility to look at the high redshift universe. There are, actually, I inverted the slides. I forgot to put the blinking. I'm sorry. There are 400 quasars that are optically selected at redshift higher than 5.7. And only 50 of them actually have been detected in X-ray after a follow-up of these 400 objects. But we were always puzzled by the fact that we were not able to find X-ray selected quasars. They were always follow-up of other. And the question was, are these type of objects not existing? What is happening? And the reason, once more, is that these objects are rare. And if you have a rare object, you need to have a larger area in order to search for them. And as I was showing before in the pencil beam surveys plot, the area that was observed by the X-ray surveys was always extremely small. So what is happening now with eROSITA? We have finally object redshift higher than 5.6. Already immediately after the observation of IFEDs and the first ERAS-1, we had the two objects. You can see them with the square around the magenta. These are all X-ray selected objects by eROSITA. And the important is this magenta object here. It is a 6.56, which is the higher redshift ever selected in X-ray, and the paper just got accepted last week, and we are preparing the press release, and the work is done by Julian Wolf, which is, by the way, also my PhD student, very proud of him. When you look at here in the plot, you see the old population of optically selected quasars, and you can see here the same representation with alpha of X, which is actually measuring the properties of type 1 AGN. And what you see with these hexagonal shapes, you see the distribution of type 1 quasars known also at the low redshift, so local object. And you see that regardless of whether they are local or they are at high redshift, they are more or less following this relation. But you also see that the objects that are X-ray detected by eROSITA, they are a little bit outside of this relation. They are brighter in X-ray, probably because there is the intervention of the jet that is enhancing the X-ray emission. But these are just hypotheses, and we are testing them. So with the two objects that were found in IFEDS, we were able to define the first X-ray luminosity function at high redshift and high luminosity, and you have it here in green, and in magenta and yellow, you have the prediction of the luminosity function that was done in the past using the sources up to redshift 3, 4 that were known before. And as you can see, we have more objects than expected, and the evolution is much gentler than what was predicted. We are already now at a further step. We have additional 5 objects detected at redshift 5.6. 3 are the ERAS-1. The objects are here in the star, and we have another 13 that are very good candidates that we are trying to have confirmation via spectroscopy. Just to say that we are populating a parameter space that was not available before, and we are really making new science in this field. One thing that I would like to bring up is that it takes time to work with our data, and I want to convince you that our results are reliable. For the people that are not familiar with the X-ray, just look at this image. You have here in pseudo green or dark green, violet, blue, you have the X-ray detection, and you have on the right side the X-ray, the optical counterparts, and it is in this case a very local galaxy. You have the object at redshift 0.6 that I was mentioning before, and this is the quasar at redshift 5.82. The point is that when you are looking for the right counterparts in X-ray, it is not just a match in RA and DEC as you will do between two optical catalogs. You need to take into account the positional accuracy of the X-ray that is depending on the X-ray flux. So here, for making you better understanding, I am plotting the positional error in X-ray versus the X-ray flux for sources detected in Chandra cosmos, XMM cosmos. And as you can see is that for Chandra, you are a sub-second positional error accuracy. You get more uncertain positional errors for XMM, and for eROSITA, you are, at least in the IFEDS field, you have the bulk of the observations are having a positional accuracy of 10 arcseconds or so, but you can also reach 30 arcseconds for few. It means that you have to find the right counterparts among the many that are available within 30 arcseconds. And thanks to N-Wave that was developed exactly for that purpose and the application of machine learning, we were able to determine the counterparts in extremely accurate way, with being pure and complete up to 95% in IFEDS, and actually at 97% of ERAS-1. And if you want later, I can tell you a bit more about that. So despite of the high energy resolution, high energy width that was mentioned at the beginning of 30 arcseconds, we are able with high confidence to determine the right counterparts, regardless the fact that the object is an AGN or a star or unresolved cluster or and so on. So we are really confident we are doing a great job. I was speaking so far about extragalactic sky. What about the contribution of eROSITA to the understanding of our galaxy or the nearby galaxies? Without understanding the Milky Way and the nearby galaxy, we cannot understand really, or say it is the only possibility that we have to understand really how galaxy formation works, and in this way implemented in galaxy evolution models. So the first thing that I would like to bring up about the Milky Way is the following. You take back the image that I was shown at the beginning, and this time I name a few of the sources, those that you can really already identify on the image without looking at the ROentgen deck of the sources. And then you do the exercise of removing all the sources and all the point sources and also the extended one. And what you have is then this smoothed image in the 0.61 kV. And what come up is this lobe in the southern part of the sky that was not known before. We knew from Rosa time that there was a northern lobe, and now that we know that there is a south one, maybe you can see there is some hint already here, but it appeared clear only with ERAS1. And if you then take these lobes and you overplot them with the Fermi bubble, you see that they actually are aligned, suggesting that this may be the trace of a past activity of our Milky Way black hole. I was mentioning before that we have the redshift for we have the spectra for our objects, and indeed we can really study temperature, we can study the metallicity of the abundances of the X-ray sky for the entire map that we have here. You have an example of how the X-ray background after removing the various sources is appearing depending on where you look. And there has been an attempt in the work of Gabriele Ponti to try to name the various components that are generating this profile in the IFEDS field, which is here. And again, today, if you had the chance to look at AstroPH, there is also an additional work that shows that essentially the gradient that is in the IFEDS area is just a matter of patchy dust material from our galaxies. And here you have the results of that work with the need of a new component, the one in green, for explaining completely the fit of our background. And of course, you can find more in the paper of Gabriele. About other events, when we were looking at the ERAS1 sky the first time, Georg Lamer found this ring, which was unusual because it was never seen before. And what we had learned is that 1 year before, there has been a maxi discovery for a new X-ray source that was classified as a black hole transient. And essentially, what we are seeing here is the dust scattering ring generated for that explosion. And 6 months after this image, essentially the ring was gone. And in the paper of Georg, you have the explanation in how this can be actually used for determining the correct distance of these objects from us. As you know, it's always difficult to determine distance in our galaxy. Another nice image is related to the Puppis-A, which is a supernova remnant. And you have a very nice analysis of the dynamics and the chemical enrichment done by Martin Meyer in this paper. What is nice to think is that you have you have the neutron star there, and this beautiful object is actually this guy, which is in front to something that is even more gigantic, which is the Vela supernova remnant. And you have also the Vela Junior, where you see it is yet another image, another supernova remnant. I would like to give you more information about this object, as I learned last week during the consortium meeting, but the paper is in preparation, so you are going to be speechless when you will see the details coming out in that paper. Here you have another supernova remnant that discovered in radio and X. This is the largest supernova ever detected, and it is a 4 degrees radius, so diameter. And so again, the size, the field of view of eROSITA is really making a huge difference when you are trying to determine these objects. Overall, we have models that explain how our galaxy evolved or is formed. We have expected numbers of supernova remnant, or expected number of nova, expected number of different type of objects. And just by counting what eROSITA is going to be able to find, we will be able to say whether or not the models were right. For example, for the supernova remnant, there were expected like 300, and instead before eROSITA, few tens were known, and now with eROSITA we are populating that parameter space. If you look back at the image that I was showing before, there is not only the fact that the ring is disappearing from one image to the next, you also have that there are plenty of objects that either were not there before, or they are getting faint, or they were there and then they disappear. And this brings me up to the third part of the beautiful features of eROSITA, namely the cadence. Because eROSITA takes 4 hours to make an entire circle, a complete circle, move off 1 degree, then another 4 hours, and it managed to look at the sky, the complete sky, in 6 times per day, and it takes 6 months to finish and make the entire whole sky. And of course, depending on where you are in the sky, either at the poles or in the equator, you have that the overlap is going to be more and more, up to the south ecliptic pole, where you have practically constant coverage, and you can really study in details the light curve of the objects. We are sensitive to different type of objects. That's showing you here the light curve in different bands for objects detected at the south ecliptic pole. Here we have 2 papers in preparations, one that explain the detection of the object, and the other that explain try to explain the properties of the object itself. And you can see really how different these objects are in the light curve. So these are 3 AGN, and each of them have a completely different light curve depending on the energy band. And we really believe that with this kind of analysis, we will be able to really understand better the physics of the black hole itself. So not only study the population and evolution, but really try to understand the physics. What is nice is that not only we overlap with Euclid for half of the field, but even one of the Euclid deep field is very close to our pole. So imagine what we will be able to do for the object that Euclid will detect. Imagine the understanding that we are going to have of the AGNs in this population, in this area of the sky. Again, on the transients that we are able to detect, this slide shows the 566 transient objects detected so far, or above a certain threshold. There are plenty of tidal disruptions events that again will be helping us understanding how the stars are stripped and destroyed and digested, if you like, by the black holes. We have a different type of temporal behavior. They are reflaring, oscillating, and so on. An important contribution of eROSITA to these transient signs is the discovery of the quasi-periodic eruptions events. Before eROSITA, 2 objects were known, and eROSITA in the first 2 passes actually have detected other 2. And this is the work that was presented in Ercodia et al. 2021. And here you can see how the objects behave in time with respect to the X-ray background. And here you can see the spectrum of the objects. when we had detected this object, we immediately triggered an ICER. And what you can see here is the periodicity of the event explained with ICER data. And I think that the period was about 11 hours, I don't remember. So hours, so yes, 11 hours. And the event is happening in a normal galaxy. We were in the first two objects were hosted in a more clear AGN dominated objects, while these two that we are detecting here are more in a star forming object. If there is an AGN activity, is extremely low. So we are with 4 objects, we are still unclear in which type of event we are speaking. We are still trying to understand the physics behind. And in these 2 papers, Ricardo tried to give some hint of what is happening. Another event that was really fantastic is the discovery of the nova reball. So about since 30 years, there are models that explain how the novas are developing, are exploding, and the models were predicting that in X-ray there should have been a fast burst, very bright, but very short. And of course, with current instrumentation, detect this kind of event was impossible. But with eROSITA, we were actually managing to detect one. So what you see here are 3 images taken with eROSITA. And as I was telling before, you take 4 hours to make a complete circle, and then you repeat it over and over. And you see that 4 hours before and 4 hours after the event, there is essentially nothing in the X-ray image. But at the moment of the event, that it's less than 4 hours long, the brightness of the object actually saturated our CCDs, and we had to make a lot of analysis in order to be able to recover the flux. And the physics is then explained in the paper of Ole in Nature. But this was definitely exciting, and see that this was happening. We were able to confirm theory that was waiting for it since 30 years. Here is just another transient. The paper got approved just last week, last Friday, I believe. And again, there is nothing in ERAS-1, ERAS-2, and ERAS-4. And in ERAS-3, you have a very bright object. And as this one, this pulsar, in reality, you have a neutron star, we RCVs, you have novas. There's really plenty of studies that we are doing with galactic compact objects in our galaxy. And of course, we also have the stars, because again, understanding the stellar population, and in particular the stars that are nearby our solar system, and we are able to understand better how our galaxy was evolved. So here you have the X-ray luminosity of the Gaia sources detected also in X-ray in the color magnitude diagram. And there is a lot of science that is going on this type of objects. But again, you needed to look at the literature if you wanted to have more details on these objects. Essentially, the work of identification is completed, and now we are starting to make the scientific analysis. I have 2 slides only. I think that I should be in time. I was mentioning before that the majority of the work done for the identification of the counterparts was done using patchwork of different surveys that were available when we started the work. But luckily, thanks to the collaboration with Chilean collaborators Alfredo Zenteno, through a program called the eROSITAs, he and the collaborators managed to observe all the sky that was missing from the legacy survey DR9, which is now in dark green, and add all the sky that was missing in order to allow us to have a complete and homogeneous coverage in optical of the eROSITA sky. With respect to legacy survey DR9, that if you probably you know, it is based on G, R, Z, and photometry in the WISE bands. The DR10 has G, R, I, Z. It is 1 magnitude deeper. It is at the depth of DES, and it has all the WISE data, including 8 years after the starting of the new WISE. So extremely homogeneous data, reduced all in the same way, and the data will become public this week already. We have one version already in use, but the public data will be there 1 week. And of course, I'm using this to connect to the fact that X-ray alone has a limited use. You really need to put it together with all the other multi-wavelengths in order to understand really what is going on. In an interview about a month ago, they were asking me, why do we need to invest in new instruments like Euclid or JWST? And I thought to explain it in this way. I hope that you like it. I think that I'm more and more convinced that is the right way of saying it. You have you are at the end of a TV series, and you have seen the final episode, which is now, the sky as it is now. And what we are doing with our work is looking at the previous episodes that will make us understanding the final episode. And we focus only in one wavelength. We are believing that all the episodes that we see are based on certain main characters. And we forget that maybe the main character is happening in another episode done with another instrument that is not our own. And only putting all this multi-wave information, all these episodes and all these main characters together, we are able to understand at the end why we are here and how we are at this point in time. One final slide. What I would like to remind you is that because eROSITA is collaborating with Foremost and Sloan 5 for 10,000 clusters and for 300,000 AGNs and later 700 with Foremost, you're going to have spectra and redshift that you can use for your science. I am practically finishing my talk, and I just wanted to zoom in our beautiful images. Once again, you can see here the supercluster of Shapley and the Virgo cluster, and these are filaments where clusters are joined later in time. And here you have the IFEDs, you have the winged that I was mentioning, and for me it is just nice to go through the images once again and enjoying the beauty of them. And with that, I am bringing you to my summary, and I just would like to remind you that we wanted to have 8 all sky surveys, so every 6 months one, so 4 years to make the entire survey. We have 2 years plus something, so 4 cycles are done, but because of the situation with Ukraine and Russia, we are in safe mode since the end of February. We are going to have eROSITA is going to be a legacy that remain unsurpassed for years for all of us to work. And these are the number of objects that we have already detected in EROS-1. And what is important for me to tell you now is that we are going to release our data in spring 2023. And here you see all the list of catalogs and images and data that we are going to provide. And with this one, I thank you, and I'm looking forward to your questions. Thank you.
Thank you, Mara. It's amazing. Great talk.
Yeah. The data allows for that.
Okay, so let's open for questions.
So are you leaving the questions also live? Because normally people feel more comfortable in having questions when they are not going to be recorded. So usually people normally close the recording for questions, but it is as you like. Young students feel better if it is not recorded.
I didn't. We haven't thought about that. Well, there is one question that apparently he doesn't mind, and so I already have his hand up. Talk to Simone about this for the next talk. Interesting point. So, Paulo Alonso.
Oh, good morning to all the colleagues and professors. And Mara, thank you so much for your lecture. It was a very instructive one. I have a question to you that's not really an astronomical question, but a project management question. I would like to know about the budget for this project for eROSITA comes only from the Max Planck Institute and other Russian institutions, or are there other universities or countries that really participate in the budget? The second question is about the time lapse of the project. How long is expected for the life of this telescope before it completes all the sky surveys that were expected since the very beginning project? So thank you so much.
Thank you, and thank you for your question. Let me stop sharing 1 second. I want to bring up a slide which I think is relevant to your question, but I do not know whether it is in a decent state. Yes, I think it is. Let me bring it up. Sorry. It is not really complete, but this give you an idea. So because I didn't, sorry, ignore me. I have to unskip it. Yeah, so this is the German collaboration, right? So MPE is the leading institute, and we had the managing the project. We are looking at the data reduction, the distribution. We build the instruments, and the funding in that case comes from DLR, the space agent, German Space Agency. We have the contribution from various universities. So you have here the various institutes that were contributing economically and also to the development of the mission. But mostly the work is really handled at my institute. Concerning the time life, there are no consumable, there is no gas that is going to be exhausted. So in principle, unless we are hit by many micro meteorites that destroy completely the CCDs, we have no problem in restarting the observation as soon as we are allowed. Remember that the planned surveys was 4 years. So again, 2 surveys per year and reaching ERAS-8 in order to do all the cosmological science that we wanted to do in order to have the precision in the cosmological parameters. We can restart and finish the missing 2 years, but remember that we also had planned for a open time for people do the follow-up of their favorite objects with eROSITA. And this is still the plan. We do not know how long it's going to be, but the idea is, again, having not only the all-sky surveys done in 2 years, starting when we can, but also having open time. But of course, it depends also when funding are remaining available. You do not know in this situation.
Mara, thank you so much. Regarding the cooperation, maybe I missed that slide. Thank you for repeating it and making it very clear. Thank you so much.
No problem. Welcome.
Okay. Any other questions? Mara, I think Simone, Reinaldo, please.
Hi, Mara. Good morning, everybody. Can you hear me?
Yes.
It's okay. Okay. I have a question about amazing results about varying AGN in the SAP.
Yeah.
I realized that you have all different patterns in the light curve for different sources, right?
Yeah.
Even they are in a different an amount of days for each one.
Yeah.
But all then have at least more than 10 days, if I'm not wrong.
Yeah. So they are closer they are on the SEP, more coverage they have. If virtually on the SEP, you are constantly having observation of 1 year essentially, because it is 6 months, so 1 year.
Right. So I'm thinking here that's a very interesting result to apply machine learning, trying to classify different objects from the light curve, right?
Yeah. Yes.
Have you think about that?
Thank you again, very nice questions. And actually, I will write down this idea. We are relying on machine learning a lot. We were, in January, we actually started a new working group that is called eROML Stats, because we realized that many of us were using machine learning and we were not communicating to each other. And we are applying it in identification not only of quasars, but of clusters, computation of masses for clusters, identification of counterparts, identification of supernova. There is plenty of analysis done now with machine learning. However, we did not apply it yet to the identification of objects based on the light curve. I think that there is an analysis of light curve done in the TDE group, so the Target Disruption Event group. There they were, they are actually having a machine learning in place, and the paper is Magliali et al. 2019, if I'm not mistaken, and they take the transient objects and classify them depending on the light curve. But we do not have anything specific for the SEP, and it will make a lot of sense given the quality of the data. So thank you for bringing it up.
Okay, thank you. Even for, that's very amazing data, because even for just a couple of days, you know, I think that's able to classify the different sources from the light curves. That's
but
amazing.
you see, if it is just 2 days, it can be that you have nothing, and then you have for a month, it is something gigantic happening. So I would rather use all the data. We should find a place, a code that take the light curve and break it in pieces, and then see whether different pieces can be identified also somewhere else. So there is something to do, but definitely it is a way to pursue it. Thank you for bringing it up.
Okay, thank you. Thank you. Bye-bye.
Okay. Rebecca?
Oh, can you hear me well?
Yes.
Okay, good. So, hi. Thank you very much for the talk. Like, it was very, very nice in all areas, right? Many things to discover. But I'm more interested on the background stability that you mentioned.
Yeah.
For me, it's really interesting. Mainly, you're focusing on diffuse sources, right? So you're really worried about how the background is interfering on all of that. So, like a first question is like, how these instrumental lines are really not interfering on the abundance measurement, for example. And is it's better controlling compared to XMM, or I'm sorry if it is too.
No, it's actually a beautiful. It is a beautiful question, because it allows me to tell things that I could not say because I had to select.
That's
so at the beginning, we were a little bit worried, because the background that we were measuring was higher than the background that was expected from simulations. And we were really worried about that. And instead, about a month ago, it appeared clearly that the background that we were measuring on EROS-1 was based on the wrong model, the wrong mass model of the instrument. So correcting for the mass model and taking into account all the components in a proper way, the background went back to where it was supposed to be. And so the lesson learned also for Tina now is you need to have a perfect understanding of the mass distribution of your objects when you are simulating the background. And this was something that was brought up like a month ago. If you are interested, I can put you in contact with the people that did the analysis in case you want to have some more clarification. Or there is a paper in SPIE that came out during the summer. The first author is Michel Feiberg. I can write to Renato, and then you can speak with Renato to the right spelling of the name. And there is all the discussion about the background. But again, if you need it, I can put you in contact with the person that did the analysis.
Yes, yeah, that's really great. Yeah, thank you. And Alec, if I may ask a second question, I saw in one of the slides you mentioned the BXA, which are the Bayesian X-ray analysis, right?
Yes.
And that's for itself really interested how you can put these priors and everything to try to solve. So have you guys been doing some working with the BXAs and also trying to working on, I don't know, try to extract more data compared to this more traditional analysis, right?
Yes. So you know that the person that brought BXA is one door beside mine, so he's working here with us. And so we are actually improving on BXA, just going on because of the data that we are getting. And yes, so every time that we need an improvement, Johannes will be able to help us. And we have actually something that we have done, but is still not public yet, is trying to analyze the X-ray spectra in general with the BXA, and also applying some machine learning and for maximizing on the errors, on the slope and such. So we are going on using the BXA and also making further analysis also on spectra that have less signal to noise than the one shown in the slide before.
Yes. Okay, thank you. Thank you very much. Thank you again for the talk. It was awesome. It was really great. Thank you.
Okay, so we're going a little bit late. I don't want to go over the talk of Sylvia soon, but before we end, I had one question that I think might be interesting for the general people, the general public, is what can people access now from eROSITA? You mentioned the 2023 goals of the data that has been reduced there, but is there general information about the data reduction line?
Thank you for bringing it up, because again, I think it is extremely important to mention that. So in terms of public data, you have under eROSITA MP and PGDA, the data that we have released last June 2021 on the calibration and performance verification reviews. So it's not only on the IFEDS area, this 140, but also the cluster, the pulsars, the supernova remnant, the star formation regions. There are plenty of areas that are available, including the software for reducing the data that we have used for generating our catalogs. So people can upload the code that we have used, run on the data and reobtain our results and learn how to do it. The next data release will be on, as I said, in year one in spring 2023. An important point is that today we had a discussion with the ESA Sky, and the IFEDS area is going to be available via ESA Sky at the beginning of December, so that people can compare our X-ray sources with other from XMM and such. And we are going to do the same also for DR1. In general, for assessing our data in advance, it is enough that you have a project in mind with data that we do not have, that only you can carry on. You can become external collaborator of our group and work with us and lead your project. Of course, if you are interested in something that we are interested in, or you have interest in something that we are already doing, then it's more difficult to become a external collaborator. But in particular, if you have your own radio data, your own optical data, you are favored special objects, and you wanted to have the X-ray flux from eROSITA, or you wanted to have an idea from a collaboration, please do not hesitate to contact us, get in contact, get the external collaborator status, and do the project right now without waiting for the data release that is going to happen in 6 months.
Thank you.
Thank you.
So I'd like to thank you again, Mara, for taking the time, and the talk was amazing. I'll have 5 more questions, but I can do it some other time. And thanks everybody for coming. And then don't miss the next talk, which is in a different Zoom link. So you have 15 minutes to rush there.
Can I have the
hope to see you soon.
Can I have the link of the other talk? You can send me via email.
I'll send you an email right now.
Okay. Thank you. Bye.
Thank you, everybody.
Thank you. Bye.